let us now discuss stream cipher. So in stream cipher, from the key, we generate a key stream first. K1, K2, K3, and the plain text blocks X1, X2, X3, those are encrypted using the corresponding bit string. So encryption of X1, with K1, encryption of X2 with K2, like that we generate the cipher text. So if you take all these KIs to be same K, then it is essentially a block cipher. So block cipher can be treated as a special case of stream cipher, where all the key stream bits or key stream digits is the same as K. Okay, KIs are K. Ki equal to K for all I. So stream cipher, another point about stream cipher is, so this plain text is divided into blocks of same length, but this block size is very small. In for stream cipher, the block size are like 1 bit or 2 bit. Okay, so block size is very small compared to the block length is very small in for stream cipher compared to block cipher. Okay. Now, some examples of stream cipher. First one is one-time pad. What we mean by one-time pad? Suppose you have a plain text bit string and key is also a bit string. So key means you have a plain text stream, bit stream M1, M2. So this is your plain text, suppose bit stream, and the key stream is K1, K2. This is also a bit stream. And this is pseudo-random bits. So what do you mean by pseudo-random bits? Sequence of pseudo-random bits means these are generating truly random sequence of bits is not feasible. If you toss a coin and if you get head, suppose we say that 1 occurs. If head, then 1, if tail, then 0. Then that way, if you toss the coin, you get a sequence of zeros and ones in that way. But whether it is a truly random bit string, so it is a truly random bit string provided your coin is unbiased. So we make an assumption that our coin is unbiased. Provided coin is unbiased, this is a truly random bit string. But how can you be sure that it is unbiased coin? So this type of assumptions we are making, so that's why it is not a truly random bit string. We call a pseudo random bit string. How much randomness it contains? There are some tests that we will discuss in time to measure how much randomness this sequence has. It has to pass certain tests. So anyway, so your bit string is M1, M2, etc. Key stream bits are K1, K2, etc. And encryption is simply MI XOR KI. So CI is generated simply bitwise XORing. MI XOR with KI. Okay, this way. So cipher text is CI. So the simple encryption is this. Decryption is simply from cipher text bits corresponding key bit you just XOR. You get MI. And this is called one-time pad, provided this sequence is truly random sequence. This K1, K2, K, this key stream is a truly random sequence. Then the cipher is called one-time pad. And if you can manage to have a truly random sequence, then this one-time pad possesses perfect secrecy. What do you mean by perfect secrecy? Perfect secrecy means probability of x given y equal to probability of x. For every plain text belongs to P and the corresponding cipher text belongs to C. So what does this mean? That means suppose you have the cipher text. You can see the cipher text. ciphertext. From the ciphertext, the probability of x given the ciphertext is same as probability of x. That means this ciphertext is not helping you to get any extra information about x. So it's information theoretic sense, there is no leakage of information about x, but by seeing the ciphertext y. So this is what this equality of probability, conditional probability, this conditional probability equal to the probability of x. We say in that case we say it possesses perfect secrecy. Okay, so this is the definition of perfect secrecy for any cipher. If this is the case, then it possesses perfect secrecy. And one-time pad possesses perfect secrecy. We can show that provided this key stream is a truly random sequence. Okay, so if you have a means to generate the key stream which is truly random sequence, then this one-time pad you get, and that possesses perfect secrecy in this sense. Another example we have seen in classical cipher. This Virginia cipher was one classical cipher where so this Virginia cipher can be treated as a stream cipher. Okay, how in Virginia cipher, let us recall this. The plain text and ciphertext space are Z26 modulo 26. So the elements are the digits 0, 1, 2 up to 25. And let L be key stream alphabet. For stream cipher, formally we will define stream cipher. So for stream cipher, we have a key stream alphabet also. That is also Z26. And for Virginia cipher, we have seen that when we discuss Virginia cipher in classical crypto systems, as a classical crypto system, there we define this Virginia cipher as a block cipher. Your plain text ciphertext space where Z26 to the power m, and key is also Z26 to the power m. So key is some m length bit string, and that bit string is added modulo 26 for plain text with each plain text block. Plain text block size is also m. Key length is m. Plain text size is also m. So you just add plain text and corresponding key modulo 26. That was your encryption. Now, when we consider Virginia cipher as a stream cipher, we consider plain text, ciphertext, plain text, and ciphertext space are to be Z26, and also key stream alphabet is also Z26. Key same m length string. Suppose your initial key, initial key is alpha 1, alpha 2, alpha m. Now, so from the key, we have to generate a key stream. For stream cipher, we have to generate a key stream. How we generate key stream? So key stream we define in this way. So your K1, K2, Km is respectively alpha 1, alpha 2, alpha m. Then next Km plus 1, Km plus 1. So K1 is alpha 1, K2 is alpha 2, Km is alpha m. This is written here. Then Km plus 1 is again alpha 1. Km plus 2 is alpha 2, so this is written here. Okay, so K twice m is alpha m, like that. So the generated key stream is K1, K2, Km, again K1, K2, Km, K1, K2, Km, like that. So it is essentially a periodic key stream, after periodic key stream with period m. So your encryption is simply your plain text is x1, x2, x3, etc. Each element here is a digit from Z26, and key stream is K1, K2, K3, etc. These are also digits. Means this is m tuple, and m tuple repeated from this key. Repeating these m tuples again and again, we get the key stream. The ciphertext is simply XORing. For Virginia cipher, it is not XORing, means x1 plus k1 modulo 26, x2 plus k2 modulo 26, x3 plus k3 modulo 26. So encryption of xi with ki we define simply xi plus ki modulo 26. And while decrypting, to decrypt this is suppose your yi, so this equal to yi, so your decryption will be xi will be equal to yi minus ki modulo 26. Okay, so Virginia cipher that we have discussed earlier, it was described as a block cipher. There, taking P and C to be Z6 to the power Z26 to the power n, K is m. And this can also be treated as a as a stream cipher by considering P and C to be Z26, K same, and alphabet key stream alphabet is, and considering your initial key to be m length string, the other the key stream is generated in this way: k1 k2 km, k1 k2 km, k1 k2 km, like that from the given key. So, so periodic stream cipher, we call it a periodic stream cipher. A periodic stream cipher with period t. What do you mean by that? That means in your key stream there is a repetition. After some period, period d, it repeats. So, ki plus d equal to kt for all I greater or equal to 1. If this is the case, then the stream cipher is called a periodic stream cipher with period t. So Virginia cipher of keyword length, your keyword length here you can see your keyword length is m. So Virginia cipher with keyword length m, this can be treated as a periodic stream cipher with period m. And key stream having short period can be cryptanalyzed. So while we design stream cipher, we need to generate key stream having large period. Okay, this is desirable. This is desirable. Key stream with large period is always desirable. Now, in this case, we have worked modulo 26. We have worked modulo 26. You can use binary alphabet, which is 26 elements, 0, 1, 2, up to 25. Instead of that, we can work with binary alphabet also. In binary alphabet, means you have to work modulo 2. Okay, so you from the given key, you generate the key stream in some way. And this key stream are binary string. So binary alphabet means your key stream is binary string. So unlike this is not binary. This is modulo 26. So in binary, if you use binary alphabet, then your key stream from the key you generate the key stream. That key stream is binary string. Your encryption, your plain text plain text is also a binary string, and your encryption is simply XORing. Okay, in binary alphabet you XOR, you get the cipher text, and from the cipher text, knowing the key stream, you can get the plain text. So this all these are whatever we have discussed so far. These are synchronous stream cipher. So we are generating the key stream, synchronous key stream. That means your key from the given key you generate the key stream that depends only on the key. Okay. So another method of generating synchronous stream cipher, synchronous key stream, it can be done using a recurrence relation of degree n. Okay, so given key k equal to alpha 1 alpha to alpha n, alpha 1 alpha to alpha n. So your ki is alpha I for I 1 to m. So k1, k2, k alpha m, km equal to alpha 1 alpha to alpha m respectively. And then from next onwards, this km plus 1 you generate in this way. Ki plus m is Cj k I plus j from 0 to m minus 1 modulo 2, where this Cj is C0, C1, Cm minus 1, C0, C1, Cm minus 1. These are elements of J2. Either they are 0 or 1. So we take a recurrence relation. We use a recurrence relation to generate the subsequent key stream. initial key stream, initial m bits of key stream is generated using the given key, and the remaining we generate using the recurrence relation. And you can see that if you take I to be m, so k1, k2, km you determine from this given key alpha 1, alpha 2, alpha m. Then km plus 1, I equal to 1, suppose from this recurrence relation, km plus 1 will be c0 k1 plus c1 k2 plus cm minus 1 km. Okay, so km plus 1 depends on the previous k values k1, k2, km. Km minus 2, km plus m plus 1 depends on k1, k2, km. Km plus 2 will depend on k2, k3, km plus 1, like that. Okay, so these CIs are given. So another way, this is another way of generating the key stream with long period. Key stream with long period. Generation of key stream with long period from a short key. So your key is here alpha 1, alpha 2, alpha m. This is called initial vector, and this constants c0, c1, cm minus 1. At c0 we take c0 to be 1, so that we get this recurrence relation is of degree n. Okay, so the key consists of not only alpha 1, alpha 2, alpha m, this initial vector, also it consists of this constant c0, c1, cm minus 1. So I have total how many variables? So there are key consists of twice m variable, twice m values, and you can generate the key stream k1, k2, etc. in this way. So k1 is alpha 1, k2 is alpha 2, km is alpha m, and then km plus 1 you generate in this way. c0 k1 plus c1 k2 plus c m minus 1 km. So this is a linear recurrence of degree m. Similarly, you can generate km plus 2. Km plus 2 depends on k2, k3, km plus 1. Km plus 3 depends on k3, k4, km plus 2. So previous m values. So that way you can generate this sequence. And what will be its period? Means after how many steps it will repeat? It depends on this constant c0, c1, cm minus 2. All these elements are either 0 or 1. C0 is 0 or 1, so all these elements belongs to Z2. So you can say that each term here, this ki's, this depends on the previous initial few values, except initial m values. All these values depends on the previous m terms. Ki plus m is a linear function of previous terms. And also we take c0 to be not equal to 0, otherwise the degree will not be m. The linear recurrence relation, this recurrence relation will have degree m provided c0 is not equal to 0. And also your initial vector alpha 1, alpha 2, alpha m, this initial values of this ki's, this cannot be 0, all 0. Otherwise, every time, if the previous k values are 0, then every time only 0 will be generated. Key stream consists of only zeros in that case. If it is, if alpha 1, alpha 2, alpha m you take to be 0 vector of length m, then only a key stream consisting of 0 you can get. So it is not equal to 0. So you can choose these constants C0, C1, Cm minus 1 in your recurrence relation in a suitable way to give rise to a periodic key stream with period 2 to the power m minus 1. 2 to the power m minus 1 means after 2 to the power m minus 1 many steps it will repeat. Before that it will never repeat. Means you generate k1, k2, your first k1, k2, km you generate by this then km plus 1, km plus 2, k twice m plus 1, like that you keep on generating. And this depending on how you choose this, you can choose these CIs in a suitable way to make this repeats, this to repeat after 2 to the power m minus 1 many steps. Okay, so your initial vector is not 0, and your key stream will be repeated only after 2 to the power m minus 1 many steps. So your period will be 2 to the power m minus 1. It depends on the choice of this CIs. So you can see that your key size, your key is very short. Your key consists of twice m values. Here m values and here m values, twice m values. M many alphas and m many CIs in this recurrence relation, used in this recurrence relation. So twice m many values. So your key size is twice m, but using this key you get a longer periodic key stream. A periodic key stream of period 2 to the power m minus 1. Maximum size is this, depending on the choice of the CIs. So this is the desirable thing. From a short key, we want to generate a key stream with long period, and this is essentially a desirable property. So we will illustrate with one example. Suppose I take m to be 4. M to be 4. So your initial vector is alpha 1, alpha 2, alpha 3, alpha 4. So it is any R tuple, and this is binary. We are working on binary. Okay, we are working on binary. Each this alpha i's, CI's, all are elements of Z2. All are elements of Z2. So okay. So suppose I take m to be 4. So m4 means your key consisting of 4 length initial vector, which is different from 0, 0, 0, 0. And suppose your recurrence relation, you generate you generate your ki's in this way. So ki plus 1 is ki plus ki plus 1. Ki plus 4 equal to ki plus ki plus 1. So this is ki plus 4 is ki plus ki plus 1. Ki plus ki plus 1 plus ki plus 2 coefficient. So ki plus 1. So this is C0 into ki. So C0 is 1. C1 into ki plus 1. C2 into ki plus 2. C2 is 0, and C3 into ki plus 3. So this is your recurrence relation. Okay, I plus 4. I plus 4 equal to C0 into ki. C1 into ki plus 1, C2 into ki plus 2, plus C3, m minus 1 is C3 into ki plus 3. So for this example, we have taken C0 is 1, C1 is 1, C2 is 0, C3 is 0. Okay, so your initial key, consisting of some 4 tuple together with this is also C0, C1, C2, C3. C0 equal to 1, C1 equal to 1, C2 0, C3 0. Okay, so you can write a code for this in C or any other language. In software, you can generate the whole key stream. You know initial vector. Suppose you take initial vector to be 1, 0, 0, 0. Any vector you can choose. Initial vector, as initial vector you can choose any vector other than 0, 0, 0, 0. Suppose I choose 1, 0, 0, 0. So what key stream you can generate? So initially this is 1, 0, 0, 0. So this is K1, K2, K3, K4. So alpha 1, alpha 2, alpha 3, alpha 4. Then next one you generate how? You generate next one by adding this one and this one. So K5, when you generate by this recurrence, K5 is K1 plus K2. So your key stream becomes 1, 0, 0, 0, this one. Then the next one, how you generate? Next one you generate using taking taking XOR of 1 and 0. So 1 and 0, 1, and the next one will be next previous these two. So 0, 0. Then this one you generate by taking, so this one, then this one you generate taking these two, so 1. Then this one you generate by taking these two, 0. Then this one you generate taking these two, XOR 0. Then this one you generate taking these two as 1. Then this one, like that. So you can continue generating this, and you can see that after means you can check after how many steps you get your initial vector to be 1 0 0 0. If you get somewhere 1 0 0 0 this pattern, then this whole thing will repeat again. Okay, you check what is the period, whether this is having period 2 to the power 4 minus 1, that means 15. After 15 many digits, whether you are getting this repetition 1 0 0 0 will come, and then it will repeat. Means not 15, 2 to the power 4 minus 1. So it is the period is 2 to the power 4 minus 1. 15. You can check that. Whether repetition is after from 16th step or before that. So it's after you can easily, you have the recurrence relation, you know initial values, so you can easily write the program to generate the entire key stream. Hardware also it is implementable. Hardware implementation of key stream using LFSR, linear feedback shift register. Okay, so linear, we are going to discuss the concept here. Later we will discuss it in more details. So what we do, so you have, so corresponding to this problem only, okay. So m equal to 4 and your recurrence relation is, you are considering the recurrence relation, linear recurrence ki plus 4 to be ki plus 1. Okay, so you can see that K5 is generated using by XORing K1 and K2. K1 and K2. So we take if m equal to 4, we take a linear feedback shift register which consists of 4 registers. So I have 4 registers. Each register contains the initial values. This is containing K1, this is containing K2, this is containing K3, this is containing K4. Each register holding 1 bit of information. 1 bit of information. Okay, so each bit is holding 1 bit of information. Now this is K5 you are generating in this way. K5 is C0 K1 plus C1 K2 plus C2 K3 plus C3 K4. For this example, C1 and C0 and C1 are 1. C0 and C1 are 1, and C2 C3 both are 0. So how to generate K5? So this contains K1, this contains K2, this contains K3, this contains K4. Initially it is alpha 1, alpha 2, alpha 3, alpha 4. And now this K1 and K2, this values, this K1. So this K1 and this C0 are AND. C0 is also B. C1, C2, C0, C1, C2, C3 are B. So K1 and C1 joined by AND gate, K2 C1 joined by AND gate, K3 C2 joined by AND gate, K4 C4 joined by AND gate. Okay, and this the output each time this output are XOR. So if you XOR these outputs, then essentially say C2 and C3 are 0. This AND gate this after this AND gates it gives you 0 here. So this K3 contributes nothing. K4 also contributes nothing. But K1 C0 is 1, C1 is 1. So whatever K1 you get, this K1 and this K2 XOR. Because C0, C1 both 1. So essentially we are generating K5 by XORing K1 plus K2 in this way. So this is the working of LFSR. If you have the recurrence relation this, you can generate this way. So this K5 you generate K5 in this way. This calculation, this K1 C0 and this is tapped with K2 C1, also tapped with K3 C2 and K4 C3. The final value whatever is generated, this is essentially the value in the recurrence, the K5. So this K5 is now take the place of K4. K4 is shifted here, takes the place of K3. K3 is shifted here. So K2 is shifted here, and K1 becomes the part of output sequence. So this is so we construct the feedback. This is your feedback. All the values are put together, and this is your feedback. This feedback is fed here, and we shift this. These values are shifted. K5 comes here, then every value shifted to the next register, and the first one, first register that contains that value is now part of the output sequence. Okay, so shift left means this way. If I draw this way, we are shifting in the left. This is called linear feedback shift register. Shifting, we are doing the shifting. A linear feedback. This is actually linear recurrence relation from where I get this value. I can calculate this value using this linear recurrence relation. That is why this is called linear feedback, and this linear feedback, and that value is put here. That value is taking place of this and shifting. This is called linear feedback. More formally, we will define it using a connection polynomial. Means connection polynomial together with the length determines that is used to define LFSR. Formally, I will define it. Okay. Now, so you can see that initially these values were K1, K2, K3, K4, K1, K2, K3, K4. Then you calculate K5, and now it becomes K2, K3. K1 is coming here as a part of output key stream, and K2, K3, K4, K5. So K5 calculated, it takes the place of K4. K4 is going into the place of K3. Then K3 is going into the place of K2. K2 is going into the place of K1. And K1 is part of the output stream. Similarly, the next iteration, K6 is calculated. K6 is calculated using this recurrence, and K6 is now take the place of K5, and all are shifted. K2 becomes the part of the output sequence. This way, you can generate, and this is essentially your key stream. Okay, so if you choose your initial vector to be different from 0, 0, 0, 0, then you can check that key stream of period 2 to the power 4 minus 1, that means 15. At most this many after this many steps it will repeat. It might repeat before that also, but certainly after 15 many steps it will repeat, because you can see that this is 4-bit string. So LFSR of length 4, it stores 4-bit string. So after 4-bit string, how many possibilities are there that can hold this? That can be held by these 4 registers. That means 2 to the power 4-bit strings. 2 to the power 4 means except 0, 0, 0, 0. So 2 to the power 4 minus 1. So after 15 many steps, after 15 many steps, you will this K1 K2 this register will come to its initial position. If it was holding initially K2 K1 K2 K3 K4 K1 K2 K3 K4, that position you again come to that position. Okay, so once you come to this position, after some time you come to this position, then everything will repeat again. You get a periodic T string. Okay, so maximum possible period with n bit LFSR is 2 to the power m minus 1. Okay, so it depends on the choice of this C0, C1, Cm minus 1 that are used in the in generating the feedback. Okay, so maximum possible period is 2 to the power m minus 1, but depending on the choice of your Cs, it may be less than that. It may be less than that. But our what is our motivation? So with a small key, a key of size this is initial vector size 4, and this C0, C1, C2, C3, these are also constants. So initial values, these values are given. So total twice as many values in the key. From that we are generating 2 to the power m minus 1 means a key stream of period 2 to the power n minus 1. Okay, and and we want to find the maximum period. Maximum period is this, maximum possible period. So what are the conditions on this LFSR, its size or its what are the conditions on these CIs so that this LFSR gives us maximum possible period. Okay, so those things are we have certain conditions. So we are going to discuss those things that defines under which circumstances we can get, under what choice of CIs we can get this maximum possible period. From a short key, we will get a key stream of period 2 to the power n minus 1. Okay, so formally we will define linear feedback shift register